this one. Oh yeah. Yeah. So, hello everyone. I would continue on the topic of the self-adjusting network as presented by Stefan this morning. I will guide you through some more detailed stuff. Let me start with a question, namely, what is a network from the mathematical perspective? Well, one might answer that it's a graph, but I claim that it actually can be viewed as two graphs. So the first one is a network graph. You can think of nodes as being just servers connected with physical wires or whatever. But the second graph, that we call the demand graph, is a graph with the nodes being servers, but the edges being messages passed between servers. And as we will see, this distinction is quite important. Consider the following example, where nodes B and D communicate, so B sending messages to D and vice versa. And note that in the physical network, which is on the left, those two nodes are not directly connected with a wire. So in order for a message to reach its destination, it needs to pass through the intermediate nodes. And the longer this transition path, the longer it takes for message to actually reach its destination. So we face some message delays in the networks, which is sometimes maybe costly. I would like to develop more on this concept. So consider the demand graph in the upper left. It's a simple demand graph with just pairwise communication of nodes. And consider a network to be a simple line, the blue line on this line in the upper right. So those nodes can be placed in many ways. So how do servers live on the line? The first option is to place them like in the lower left. So communicating pairs are placed next to each other. And that's good, because the other option is to place communicating pairs far apart from each other. And you can see those red edges representing message paths. They become stretched. And if we count the total length of red edges, in the first case we get theta of n length, where n is the number of nodes we have. And in the second case it becomes quadratic. So the difference is considerable, I would say, but one might still be skeptical and ask whether this is relevant in practice and whether it's not a made-up theoretical example. So I will claim that it is not, and I refer to the studies made by Facebook and Microsoft. Here on the slide you can see two matrices representing communication between servers in the data center. The main takeaway from those matrices is the fact that they're far away from being uniform. Okay, so one can see different patterns appearing in the matrices. Some nodes communicate intensively, some nodes do not communicate at all, and our claim is that that can be exploited to improve the real-world systems. Speaking of our model, we consider a dynamic scenario that allows us not to make any assumptions on the actual communication patterns. So we can assume that we observe the system from its very beginning, starting from no information at all. Then we see the first message being passed. Then we see a first message being passed between two nodes. The other message, the third message between two nodes we already knew are communicating. And so we end up with a weighted graph where edges represent communication and weights represent the intensity of communication, if you wish. And here comes the concept of adjustment. Recall our bad example of communicating nodes being placed far apart from each other. So I'm claiming that with the help of adjustment, we can make this picture look better. So what I will do, I will take this B node and will bring it towards its partner, namely the A node. And I will do it by forming swaps like this. So I'm dragging the B node through the whole network, so it ends up being close to its partner. And this picture is better. It's still not perfect because, for example, C and D are far away, but it's better from what we have started with. And yeah, this is the adjustment in short. So now we are ready to discuss formally the model. What we have is we have a demand graph representing messages. We say that it is of known type, meaning of known family, like tree, click, cycle, etc. We also have a network linear graph, which is known. We maintain a configuration, so we place servers on the line one way or another. And requests come with time. A request is a message sent from one server to another. So it can be viewed as an edge of the demand graph. And before serving the request, we can perform some swaps as we did in the previous slide. And for each such swap, we pay a unit cost, just an abstract cost. And after we are done with our swaps, we serve the request. By that, I just mean that we pay the distance between the images of two nodes on the line. So the intuition is, if nodes are far, request is expensive. If they are close, request is cheap. And our goal is to design such an algorithm that would combine both cheap reconfiguration and low-cost request serving.
Sorry?
Yep.
So the distance is again like graph distance, so that means we can either swap or pay the distance, doesn't matter.
Yes, yes. But in the future it might matter. Yeah. If you're talking about the single request, it does not. But if two nodes will send 100 messages to each other, you'd better bring them closer. Yeah. Okay. So what is known on the topic? Well, not much. The paper this problem was introduced is called Self-Adjusting Linear Network by Arvind Vision and Stefan Schmidt. And in this paper, authors considered two graphs. The first one, the demand graph is linear, and the network graph is also linear. So one might be confused at this point, asking whether it's a trivial problem to configure a line on the line. So let me remind you that from the very beginning, we don't know how exactly the demand is structured. So here on the picture in the middle, we have the demand graph being a line, but it's far away from being an optimal line on the network. Okay, so in the papers there are two theorems. First one is saying that there is an algorithm such that it pays n squared log n for the migrations and spends a constant cost for serving the requests. So this is an upper bound if you wish. And also authors show that this algorithm is in a sense optimal, providing the corresponding lower bound, which says whether whatever algorithm you come up with, there would be a cruel sequence of requests called sigma in the statement. Why is it cruel? Well, because there are n squared requests in the sigma, but your algorithm would pay n squared log n for that. Meaning you serve the request for the cost log n in average, and you cannot do better. So this is result by Arvind et al. What is our result? We made a step further, and we no longer consider a line demand graph, but rather we consider a 2 times n grid, a demand graph depicted here in the upper left. And I will refer to this graph as a ladder graph, because it looks like a ladder. So our theorem is a straightforward analogy to the previous theorem, and it says that there is an algorithm for the ladder which also spends n squared log n cost for doing swaps or migrations, and it still pays a constant cost for serving the request. So one might ask, what about the lower bound in this case? And I would reply that the lower bound is not really needed here, because the ladder demand graph by itself contains the line demand graph, and therefore any lower bound which holds for the line is also applicable for the ladder. Okay, so let me now discuss the details of our algorithm. And I would like to start with a slightly simpler problem, which is an offline embedding. So assume you have some subgraph of a letter, depicted here on the upper left, for example, and we want to embed it or configure it to the network. We will do it in 2 steps. So we first embed a letter subgraph into the letter, and then we embed a letter into the line. So the result composition, the result embedding is just the composition of those 2. And I point out that the letter embedding can be done trivially by just embedding a letter level by level. So it's not the interesting problem. The interesting problem is to embed a subgraph of a letter into the letter. And I will go through more details on that now. So consider this a nice letter subgraph on the slide. And so if you look at it a bit more precisely, spending a bit more time, you will notice that it actually can be decomposed into cycles and trees, as shown here on the slide. So we call such a concept a cycle tree decomposition. And the fact is it can be efficiently computed, meaning in polynomial time. So how do we use that to embed into the letter? Well, it turns out that trees in a cycle tree decomposition have a very well understood structure, and the key concept is a trunk core, depicted here in blue. So what is a trunk core? It's a line graph, a line subgraph of a tree, such that if you remove it from the tree, what you're left with is only line graphs. So very, very simple structure. Let me introduce a little bit of terminology here. Those line graphs that are connected to the inner nodes of the trunk core, they are called inner graphs, and those line graphs that are connected to the end nodes of the trunk core, they are called exit graphs. So how do we embed a tree into the... Yep. So I only have 5 minutes. Yes, so the tree can be embedded using this decomposition. It's quite straightforwardly done. After that, what we do to embed the component, we decompose it in a cycle tree decompositions. We embed trees in cycles, and we glue them together. Pretty intuitive. So let us now discuss the online scenario, because it was the initial problem. We have requests coming with time, and we have 3 cases here. So the first one is, we already know the edge, we already know that nodes were communicating. In this case, we say that our current embedding is good enough and we change nothing. And we have 2 other cases, which is edges with a known connectivity component, and it is within 2 different connectivity components. So let us go through these 2 cases. If the edge is within 1 connectivity component, it means we have a cycle, because 2 nodes are already reachable. So we form a cycle and we embed it, name the trivial. If the edge is between 2 connectivity components, we need to apply a clever strategy, because those 2 can be embedded quite far away from each other on the line. So the approach here is to bring the smaller component towards the bigger one, so the cost of movement would be amortized eventually. And then we just perform some adjustments inside the bigger components to make sure that the smaller one connects well to it. Okay, and how much does that cost for us? How costly is this strategy? So this is a picture of forming a cycle, and in order to obtain this cycle, some nodes might travel quite a long way from left to right in this case, and we cannot control this movement, but we claim that this one is amortized because those nodes were not on the cycle, and now they are. So this happens only once, and we therefore have n nodes one time on a cycle moving distance of n, which is n squared. And in case of reconfiguring 2 different components, there is a classical technique here of bringing a smaller one to a bigger one. That results in s squared log n, so this is the real bottleneck of the algorithm. And the adjustment of the bigger component I mentioned, without going into the details, they are amortized the same as I just mentioned. Okay, so that's it. Let me conclude. So in our paper, we addressed the challenge of fitting a demand graph into the network graph. We allowed ourselves online reconfigurations, so to make the adjustments on the fly. We considered ladder demand graph and the line network, and we came up with an optimal algorithm through going through the ladder subgraph analysis. And I would like to emphasize that this is a step to the general case of n times n grid. So that's a good start, but there are lots of things to be done in this area. Thank you for listening, and I will be happy to answer your questions.
Questions? When you talk about the grid, is it embedding the grid in a line or embedding the grid in a grid?
Yeah, that's a good question. So I believe that both cases are interesting. What I want to mention is that embedding grid to grid, even in the offline case, so where you just know the graph, where you don't need to adjust online, it's an NP-hard problem. So if you have a tree and you want to figure out whether it can be embedded into the grid, it's NP-complete, if the answer is yes or no. So that would be more challenging, and there is more ways to start from embedding it into the line, I guess.